Okay, we continue our exercises. So we will, before I start this set of exercises, this is the another proof of the duality for LP spaces, 1 less than p less than infinity. So that requires some notions from functional analysis, which I briefly recall. So V is Banach space, then V prime equals dual space. That means the space of all continuous linear functionals. So then V double prime is again dual of V prime. So if you take x in V, then f in V prime, then f of V, f of x is less than or equal to norm f times norm x, and therefore this f going to f of x is a continuous linear functional. So we will call this Jx of f is the evaluation f of x. So Jx belongs to V double prime. In fact, norm of Jx is the same as norm of x. Okay, so V is reflexive if J going to V double prime is onto. That means every continuous linear functional on V dash occurs only in this fashion, namely it should be of the form Jx. Then it's supposed to be a reflexive space, and then closed subspace of reflexive space is reflexive. Isometric, isomorphic image of a reflexive space is reflexive. Now V is said to be uniformly convex. That means the unit ball bulges uniformly. If you take the ball in R2, then it is in Rn with the Euclidean norm, then it's a nice round ball. But if you take it with the 1 norm or the infinity norm, then it will have a lot of flat portions. So it is said to be uniformly convex if it bulges uniformly in all directions. So this is a geometric property of the norm. Given epsilon positive, there exists a delta positive such that norm f, norm x equal to norm y equal to 1, norm of x minus y greater than or equal to epsilon implies norm of x plus y by 2 is less than 1 minus delta. So there is, if the 2 points on the boundary of the unit ball are a certain minimum distance apart, then their midpoint must be well inside the ball. That is the notion of uniform convergence. And then there is the theorem V uniformly convex implies V reflexive. So these are the things which we need to recall in order to do the subsequent exercises, which uses the methods of functional analysis and gives you a proof of the theorem. Okay, so 5. So the exercise 5, I believe. Okay, so show that if alpha beta are greater than or equal to 0, then and 2 less than or equal to p less than infinity, then alpha square plus beta square to the p by 2 is greater than or equal to alpha power p plus beta power p. Okay, solution. So we look at the function phi x equals x square plus 1 to the power of p by 2 minus x power p minus 1 for x greater or equal to 0. Then phi of 0 is of course 0, and phi dashed of x equal to px into x squared plus 1 to the p minus 2 by 2 minus px power p minus 1. And if x is positive, p bigger than or equal to 2, this will be greater than 0 for if x is strictly positive. Okay, so this is greater than 0. Okay, so this means that phi is an increasing function. So you have x squared plus 1 to the p by 2 is greater or equal to x power p plus 1. Now you put if beta or alpha are not 0, if one of them is 0, there's nothing to prove. So you take x equals alpha by beta. Then you will get from this that whatever the inequality you want. Okay, so that is the solution of this. So B, 2 less than or equal to P less than infinity, and XS mu measure space, F G in LP mu. Show that norm F plus G by 2 LP whole power P plus norm F minus G by 2 P whole power P is less than or equal to 1/2 norm FP plus norm GP. This is called Clarkson's inequality. Okay, so mod fx plus gx by 2 power p plus mod fx minus gx by 2 power p is less than or equal to, so a power p, alpha power p plus beta power p is less than or equal to alpha square plus beta square power p by 2. So by a, this is less than or equal to mod fx plus gx by 2 power square plus mod fx minus gx by 2 whole square power p by 2. And if the inside, if you simplify, this becomes mod fx square plus gx square by 2 whole power p by 2. Now, if p is greater or equal to 2, then you have t going to p by 2, t power p by 2 is convex. Take the second derivative, that's positive number because p is bigger than 2, therefore this is a convex function. So by definition of convex function, something in the midpoint is less than or equal to the average. So this is 1/2 of mod fx square power p by 2, which is mod fx power p plus similarly mod gx power p. Now integrate both sides to get double star. Okay, so then this is the Clarkson's inequality. deduce that LP mu is uniformly convex, and as I said, this implies reflexive for 2 less than equal to p less than infinity. So, solution: norm Fp equals norm Gp equal to 1 and epsilon greater than 0, norm F minus Gp bigger than or equal to epsilon. Then from by double star, by Clarkson's inequality, you have norm F plus G by 2 P whole power P is less than or equal to 1/2 of norm Fp plus norm Gp. Each of this is 1, so you get 1 minus, so this one is greater than epsilon by 2 power p. Okay, norm F minus G is bigger than epsilon, so this is greater than F minus Gp, so you have minus epsilon by 2 whole power p. And you can write this as 1 minus delta whole power p for some delta greater than 0. Then, of course, norm F plus G by 2 P is less than 1 minus delta. Therefore, LP mu is uniformly So what is delta? Delta is equal to 1 minus epsilon by 2 power p whole power 1 by p. Okay, so this is the number which you have for delta. Six. Let 1 less than p less than infinity, p dash conjugate exponent, and x s mu measure space. A, if G belongs to LP dash mu, define fx to be equal to, we have done this kind of thing before, mod gx to the power of p dash minus 2 gx if gx is not 0, and 0 if gx equal to 0. Why am I doing this? Because if p dash minus 2 may be a negative exponent, so we don't want things blowing up. So that is why we are defining it this way. Okay, then show that f belongs to LP mu. So that's easy. So mod f power p equals mod g power pp dash when you take mod f, then you get mod g to the p dash minus 1 whole power p, which is equal to mod g to the pp dash minus p, which is equal to mod g power p dash, because 1 by p plus 1 by p dash equal to 1. So they call that. Okay, now this is integrable, and therefore you have that f belongs to LP. B, G in LP dash mu, Tg of f, definition is integral fg d mu is over X for every F in LP mu. Then TG belongs to LP mu dash and norm TG is equal to norm GP dash. You remember we did this with lot of lemmas in the case of finite measure spaces. Okay, so now we are doing it in the general case. Okay, so we have the TG mod TGF is less than equal to norm F P norm GP dash. This is held as inequality. And therefore this implies TG belongs to LP mu dash and norm TG is less than equal to norm G P dash. But F in LP mu as in A, then TG of F equals integral Fg d mu over X, but Fg equals mod G to the power of P dash. So this is equal to integral over X mod G to the P dash d mu. So norm mod of TG F by norm Fp is equal to integral mod G to the P dash d mu over X by norm Fp is what? Norm F is the integral of mod Fp power 1 by P, but mod Fp we already know is mod G P dash. So this is integral over X mod G P dash d mu power 1 by P CFA. And therefore this is equal to integral over X mod G P dash d mu power 1 minus 1 by P, which is equal to, and 1 minus 1 by P is equal to 1 by P dash, and therefore this is equal to norm G P dash. So the supremum, what is the norm of the linear transformation? It's the supremum of all such quotients that is less than or equal to norm G P dash we have already seen here, and now we are producing an element for which it is actually achieved. So this implies norm TG equals norm G P dash. C deduce that LP mu is reflexive for all 1 less than P less than infinity. So we know that, so solution LP mu is reflexive if 2 less than or equal to P less than infinity. So now from LP dash mu to LP mu dash we have a mapping T of G equals TG. Okay, and this is an isometry since norm TG is equal to norm G P dash. Okay, so T of LP dash mu is isometrically is a closed subspace of LP mu dash. And if 1 less than p less than equal to 2, this implies 1 less than p dash less than equal to 2, this implies 2 less than equal to p less than infinity. Okay, so this means that now LP mu reflexive implies LP mu dash also reflexive, and this implies T of LP dash mu reflexive implies LP dash mu reflexive, because it is T is an isometry. Therefore, for all 1 less than p dash less than infinity, less than or equal to 2, LP dash mu reflexive. So that is LP mu reflexive for all 1 less than p less than or equal less than infinity. D LP mu p dash mu is isometrically isomorphic to LP mu dash. So T from LP dash mu to LP mu dash is an isometry. T of G equal to Tg. Okay, so enough to show T is on 2. So that will complete the problem. So assume the contrary. Assume not. So this implies there exists a phi in LP mu dashed, and phi is not equal to Tg for any G in LP dash mu. That is, phi does not belong to image of T, but image of T is a closed subspace. So by Hahn-Banach theorem, there exists a capital phi in LP mu double dash. Capital phi of small phi is not 0, and capital phi of Tg equal to 0 for all G in LP dash mu. Okay, so that is, it vanishes on the image of T but does not vanish completely. But LP mu double dash is the same as LP mu. That is, there exists a F in LP mu such that phi of F is not 0, but integral over x Fg d mu equal to 0 for all G in LP dash. Now again we play the same trick as we did before. Take G equals to mod F to the P minus 2 F if Gx, sorry, if Fx is not 0, and 0 if Fx equal to 0. then G belongs to LP dash mu, and therefore integral Fg d mu over x is nothing but integral mod f power p d mu, and that is mod f power p d mu. Okay, but this is equal to 0. This implies that f equal to 0 implies phi of f is 0, which is a contradiction. Hence, T is onto, that is LP dash mu is isometrically isomorphic to LP mu dash isometric isomorphism. And you have Tg, so every Tg of f equal to integral Fg d mu over x, and norm G, norm of Tg equals norm G p dash. So this is the theorem which we proved, the Riesz representation theorem. So for every continuous linear functional on LP mu is of the form T of the form like this. Okay, so here, so for 1 less than p less than infinity, no need for sigma finiteness. That is the beauty of this proof. Seven. Let f belong to L1 of Rn. Assume for every phi belonging to C infinity of Rn, C infinity functions with compact support, such that phi is non-negative, we have integral over Rn f phi dmn is greater or equal to 0. Show that f is greater or equal to 0 almost everywhere. Solution. We take rho epsilon mollifiers. Then f star rho epsilon of x is equal to integral over Rn f of y rho epsilon of x minus y. F is convolution is commutative, so you can write it in any way you like, dmny. Now, if you take y going to rho epsilon of x minus y, this is a C infinity function, it is greater or equal to 0 and compact support contained in B closure set of center x and radius epsilon, because you have just translated the rho epsilon by x minus y, and therefore this has the center at x and epsilon greater or equal to 0. So this implies that f star rho epsilon of x is greater or equal to 0. But we know f star rho epsilon converges to f in L1 of Rn. implies there exists a subsequence epsilon k tending to 0 such that f star rho of epsilon k converges to f pointwise almost everywhere. Okay, and since this is greater than or equal to 0 pointwise and it converges to f, so this implies that fx is greater than or equal to 0 almost everywhere. Okay, so that proves this theorem. So it's a very nice application of the convolution idea, a different kind of application. So namely, if these integrals are all non-negative for non-negative functions, then the function itself has to be non-negative almost everywhere. Okay, so we will conclude the exercises with this. So the next very short topic I want to deal with next time is about the change of variable formula. We have seen particular cases of it, so I would like to give you the general formula for that, which we will see next time.